Download this code from codegive.com, link in the description below. OK, let's dive deep into analyzing hotspot crashes. This is a comprehensive guide, covering the crash dumps, tools, and techniques for troubleshooting JVM crashes in Java applications. It's a complex topic, so be prepared for some technical details. Understanding hotspot crashes and the crash dump, hs_error_pid.log. When the JVM encounters a fatal error, it often generates a crash dump file, typically named hs_error_pid.log, where PID is the process ID of the JVM. This file is crucial for diagnosing the cause of the crash. It contains a wealth of information. Basic information, JVM version, operating system, CPU architecture, number of processors, memory details. Error details, the specific signal or exception that caused the crash, example sigsegv, sigabrt, out-of-memory error. Thread information, stack traces of all threads running in the JVM at the time of the crash. This is often the most important part. Heap information, summary of the heap usage, including free and used space. GC information, details about garbage collection, GC, activity, algorithms used, and memory pool status. Native library information, loaded native libraries, DLLs or shared objects, and their memory addresses. VM flags, JVM arguments and options used when starting the JVM. Registers, CPU registers, program counter, stack pointer, etc., at the time of the crash, useful for native crashes. Assembly code, disassembled code around the point of the crash, also more useful for native crashes. Common causes of hotspot crashes. Before we delve into analysis, let's identify common culprits. 1. Native code issues. Memory corruption. Writing to invalid memory locations in native libraries, example using JNI. This is a frequent cause. Null pointer difference. Trying to access memory through a null pointer in native code. Buffer overflows. Writing beyond the bounds of allocated memory in native code. Incorrect data types. Mismatched data types between Java and native code, example using agent in Java but treating it as a long in native code. Resource leaks. Failing to release native resources, memory, file handles, etc. 2. JVM bugs. Rare, but the JVM itself can have bugs that lead to crashes. 3. Hardware issues. Memory errors, CPU instability, etc., can also manifest as JVM crashes. 4. Out-of-memory error, OOME. While usually manifested as an exception, severe OOMEs can sometimes trigger crashes if they occur at critical points within the JVM. 5. Stack overflow error. Excessive recursion or very large stack allocation can exceed the stack size limit and cause crash. 6. JIT compiler bugs. The just-in-time, JIT, compiler can sometimes generate incorrect machine code. These are harder to debug, but disabling JIT compilation, java.compiler = none, can help isolate the problem. 7. Concurrent modification issues. If multiple threads concurrently modify data structures without proper synchronization, it can lead to inconsistent state and crashes. 8. Deadlocks. Deadlocks can sometimes indirectly trigger crashes, especially if they occur during critical JVM operations. Analyzing the hs_error_pid.log file, step by step. Let's break down the process of analyzing a hs_error_pid.log file. We'll use a fictitious example to illustrate. 1. Examine the basic information ****. Open the hs_error_pid.log file in a text editor. Start by looking at the top section. Example. *signal/exception *sigsegv, segmentation fault, indicates a memory access violation. This is very common in native code issues. Other signals like sigabrt, abort signal, means abnormal termination. *PC, program counter 0x000007F242D4394DD is the memory address where the crash occurred. *problematic frame *libnative.so plus 0x14DD native function plus 0x2D. This tells you which library, libnative.so, and function, native function, were involved, along with an offset, 0x14DD. This is extremely important because it often pinpoints the location of the bug in the native code. *JRE version /Java VM * check for known issues with that specific version. 2. Thread information ****. The threads section lists all threads. Look for the thread that caused the crash. This is often indicated in the current thread section, or you can correlate it with the TID, thread ID, from the initial error message. *current thread identifies the thread that encountered the error. In this case, it's a VM thread. *siginfo gives more details about the signal. *sigsegv_mapper typically means the address si_address, here, 0x0000000000000000 is not mapped into the process's address space, i.e., a null pointer dereference. *stack, the stack trace is crucial. It shows the sequence of function calls that led to the crash. Notice the C, J, and V prefixes. *C, native code frame. *J, interpreted Java code frame. *V, VM, JVM, code frame. 3. Analyze the stack trace ***. Focus on the stack trace of the crashing thread. Start from the top and work your way down. *native frames * look for any C frames related to your own native libraries. In the above example, the first C frame points to libnative.so, which indicates some native code issue. *Java frames * identify the Java code that calls the native function, the J frames before the C frame. In this example it is com_example.native_class.call_native_function. *root cause * the stack trace usually provides valuable clues about where the error originated. In this case, the problem appears to stem from native function in libnative.so, called from Java code. 4. Examine the VM flags ***. The VM flags section shows the JVM options used. *heap size * check if the heap size is sufficient. Insufficient heap can sometimes indirectly cause crashes. *GC algorithms * the GC algorithms used, example XX plus use G1GC, can sometimes be relevant if the crash is related to garbage collection. Unusual flags * look for any custom JVM options that might be contributing to the problem. 5. Heap information ***. The heap section gives you a snapshot of the heap usage. *heap usage * check if the heap is nearly full or if there are signs of excessive GC activity. 6. Native library information ***. The dynamic libraries section lists the loaded native libraries. Library addresses * the memory addresses of the libraries are listed here. You can use these addresses, combined with the offset from the problematic frame, to pinpoint the exact instruction that caused the crash within the library. Debugging with GDB, for native code. If the crash involves native code, which it often does, GDB, GNU Debugger, is your best friend. 1. Install GDB*. If you don't have it already, install GDB on your system. 2. Compile with debug information*. When compiling your native code, example your C/C++JNI library, make sure to include debug information using the G flag. This is critical. Without debug information, GDB will only show you assembly code, not the source code. 3. Start GDB*. Attach GDB to the running Java process. You'll need the process ID from the hs_error_pid.log file. 4. Load symbols*. Load the symbols from your native library. Replace /path/to/libnative.so with the actual path to your library. *base_address is the starting address of the library, found in the Dynamic Libraries section of the hs_error_pid.log. For example, from earlier example. Then base address is 0x0007f242d43800. 5. Set a breakpoint*. Set a breakpoint at the function and offset from the problematic frame. In our example, it was native function plus 0x2d. 6. Continue execution*. Tell GDB to continue running the process. If the crash is reproducible, GDB will hit your breakpoint just before the crash occurs. 7. Inspect variables*. Use GDB commands to inspect variables, memory, and the call stack. *print variable, prints the value of a variable. *backtrace, displays the call stack. *info locals, shows local variables. *x/format address, examines memory at the given address. For example, x/10i$PC displays the next 10 instructions at the program counter. x/s address displays a string at the given address. 8. Step through code*. Use next, step, and finish to step through the code and understand what's happening. Example code, native with JNI. Let's create a simple example of a native code crash using JNI. Java code, myapp.java. Native code, my_native.c. 1. Generate the JNI header ***. This will create com_example_native class.h. 2. Compile the native code ***. Important ***. G is crucial for debugging. *shared creates a shared library, DLL or .so. *fpic, position independent code, is needed for shared libraries. $i$java_home/include and $i$java_home/include/linux, or equivalent, are needed to find the jni.h header file. Adjust the paths as needed. 3. Run the Java program ***. This will crash with a sigsegv or similar signal, and a hs_error_pid.log file will be created. 4. Analyze the crash dump and debug with GDB ***. Open the hs_error_pid.log. Identify the crashing thread, the problematic frame, which should point to libnative.so and java_com_example_native class_call native a function, and the library address. Start GDB, GDB ppid. Add symbols, add symbol file /libnative.so base_address, replace with the correct path and base address. Set a breakpoint, break java_com_example_native class_call native a function, you might need to add an offset if the crash occurs at a specific instruction. Asterisk continue, continue. Asterisk examine variables, print PTR, you'll see that it's null. Key takeaways and best practices. Asterisk reproducibility. Asterisk try to reproduce the crash consistently. This makes debugging much easier. Asterisk reduce complexity. Asterisk simplify your code to isolate the problem. Remove unnecessary features and dependencies. Asterisk logging. Asterisk add extensive logging, both in Java and native code, to track the program's execution flow. Asterisk defensive programming. Asterisk in native code, always check for null pointers, validate input parameters, and handle errors gracefully. Asterisk use memory checkers. Asterisk tools like valgrind, for Linux, and address sanitizer, ASAN, can detect memory errors in native code. They're extremely helpful. Asterisk keep JVM and libraries updated. Asterisk bugs are sometimes fixed in newer versions. Asterisk test JNI thoroughly. Asterisk JNI code is notoriously prone to errors. Write comprehensive unit tests. Asterisk understand JNI data types. Asterisk be very careful about data type conversions between Java and native code. Asterisk use JNI best practices. Asterisk always use new global ref or new weak global ref when storing JObject across the calls. Release the object using delete global ref or delete weak global ref when it's no longer needed. Failing to do so can lead to memory leak. Asterisk resource management. Asterisk properly allocate and deallocate resources in native code, memory, file handles, etc. Asterisk sanitize input. Asterisk always validate and sanitize input data that comes from Java before using it in native code to prevent vulnerabilities. This detailed guide should equip you with the knowledge and tools to tackle hotspot crashes effectively. Good luck debugging. Remember to carefully examine the hs_error_pid.log file, use GDB for native code issues, and follow best practices for JNI programming.